In the previous video, in the video on Poisson distribution, I've made a mention after defining the limitations and after defining how Poisson distribution, how a variable takes Poisson distribution, I made a mention that Poisson distribution is the limiting case of binomial distribution. Let's see how it becomes a limiting case. We all know that the formula for binomial distribution is, out of n trials, probability of getting R successes is given by the formula NCR P power R Q power n minus R. Okay. Now let's go into the expansion of the binomial distribution formula. NCR we all know n factorial by NCR is written like this, n factorial by R factorial into n minus R factorial. Okay. So I'll be expanding. Of course, there's another version of it. Suppose if I have 7C3, how do I write it? 7 into 6 into 5 by 3 into 2 into 1. There's another version where this n minus R terms gets cancelled off. Only that terms which are there in the, which are not there in n minus R come here. Okay, so accordingly, I'm writing the formula n into n minus 1 into n minus 2. Okay, till where I'll be having n minus R minus 1. Till there I'll be having the terms by R factorial. The second version of the formula is what I'm taking. P power R is there. Q also I'm writing in terms of R. 1 minus P. Q is nothing but 1 minus P according to binomial distribution. So I'm writing it like this, right? Now, next, n according to Poisson's, I said when n is very large and then P is very small, n into P, the product, we take it to be lambda, the averaging parameter, or the Poisson parameter, and then lambda is equal to np. So I'll rewrite it, p is equal to lambda by n or n is equal to lambda by p accordingly and use it in this formula because I have to show that it's a limiting case, right? Okay. So now what I'll do is I'll replace n is equal to lambda by p in the formula. So I'll have lambda by p minus 1, lambda by p minus 2, and so on, lambda by p minus r plus 1. I'll have, okay, by r factorial is anyways there. Apart from this, I'll just erase this part to avoid ambiguity in the expansion. Okay, into p power r, this term can be written as 1 minus p power n by 1 minus p power r. Okay, yeah. Now, if you take out all the p's common, how many p's will come? Lambda by p is anyways there. If I take p's common, then what I'll, in the first term, what I'll be having? 1 by p I'll be having. Second term also 1 by p. Till where I'll be having? Till r minus 1. So, p power r minus 1 p's will be there. Okay. So, if I take p common and take the LCM, I'll be having lambda minus p into lambda minus 2p into lambda minus 2r plus 2. Okay, just a second. 2p into r minus 1 into p is what I will have. Okay, so p into p power r minus 1 will give me what? P power r only. Right? Now I'll be having r factorial in the denominator. P power r is also there. Also this term 1 minus p power n by 1 minus p power r. This term is also there. Okay, this is n power n. This is power r. Okay. Now if this p goes to the denominator, lambda lambda by p power r I will have. Okay, this into this. Lambda minus p, lambda minus 2p, and so on, lambda minus r minus 1 into p, lambda minus r minus 1 into p. Okay. By r factorial is what I have. Of course, there's a p power r. These two get cancelled off. And from this also, I'll be replacing P with lambda by n. What is P? Lambda by n. I'll be replacing that in this. Okay, in a Q part. Okay. So finally, what I have? Lambda into lambda minus P into lambda minus 2P and so on. Lambda minus R minus 1 into P by R factorial is anyways there into P power R and P power R got cancelled off. 1 minus lambda by n whole power n by 1 minus P power R. Let it be like this only. Why? Because this is the standard formula which you have learned in your +2, that is limit n tending to infinity 1 plus 1 by n. Okay. 1 plus 1 by n power n as n tends to infinity will tend to e. So accordingly, I will write this. Okay. So this term will be this one as n tends to infinity will be something else. But first let me write the condition. As n tends to infinity, what happens? As n tends to infinity, lambda is equal to np na. Okay, as n tends to infinity, what happens to p? P tends to 0. So wherever p's are there, all of them will go to 0, right? So what I will have will be, how many times lambda is there? Just check here. Lambda, of course, this is r minus 1 times till here to here, and this is r minus 1 into lambda power 1. Okay, what I'm saying is lambda power 1 into lambda power r minus 1. R minus 1 lambdas are there. Okay, by r factorial. This numerator gets transformed to e power minus lambda. Because both are pluses here, I've got e. Because both are minuses here, I mean I have a minus here and there's a lambda in the place. E power 1 this is. Here, okay, here in the place of 1 I have lambda. So e power minus also is there. So I'll rewrite this as a plus into minus lambda. Fine. Okay, so this minus lambda goes to the e power. Okay, now what happens to the denominator? Limit n tending to infinity 1 minus p power r. As long as r is finite. Is r finite? Yes, it is finite only. Because you are taking out of 10 some 7. If you are asking, then 7 is finite only. Now, as long as r is finite, as n tends to infinity, p tends to 0. So p tends to 0. So this term also tends to, I mean, p tends to 0. So this term tends to 1. 1 power r or 1. Why? Because r is finite. If it is infinite, then things will change again. P tends to 0. So this term becomes 0. I'll be left with 1. So in the denominator, I have only 1. Finally, you can check. What's that? Lambda power r by r factorial into e power minus lambda. I have considered binomial distribution. P of x is equal to r. I have considered. Okay, I said it's a limiting case. What's the limiting case? The limit is as n tends to infinity. Whenever you are saying a limiting case, that means you are considering the case when n tends to infinity. That's why I have considered here n tends to infinity. I have rearranged things. After rearranging, I have considered as n tends to infinity. Okay, p is tending to 0. You can check here. As n tends to infinity, what happens to p? I have rewritten p here. In the denominator, if this is an infinity, something by a large quantity will tend to 0, right? So p is tending to 0. And since r is finite, 1 minus p power r will tend to 1. P is 0, so it will tend to 1. That's how Poisson distribution will be a limiting case of binomial distribution. That's how when we consider binomial distribution and apply n tends to infinity, you will be getting Poisson distribution. Okay. This is it. I will share some more things about binomial in the next video.